Good day, students. Today we continue our lectures, physics, and now we talk about characteristic of lights. Interference of light waves, coherence. Interference of light is used in medicine in interferometers, interference microscopes, a determination of sensitivity of retina, and in many other cases. Superposition of two or several waves resulting to steady time amplification of oscillation in some points of space and attenuation others is known as interference. In usual conditions, often there is a superposition of light waves from various sources, but interference of light is not observed. Each such source, for example, a lamp, a flame, the sun, etc., represents a set of big number of radiating atoms. Difference of phases of oscillations which radiate such source will not be constant and quickly and randomly change in time. The interference of light can arise only from the coordinated coherent sources, which provide constant in time difference of phases of composed waves in various points. The waves adjacent to this condition are known as coherent. It is at identical frequency length of wave have the constant phase difference. The interference could be carried out from two sine waves of identical frequency. It's possible to receive coherent waves having divided a wave from one source on two parts by reflection or refraction, and then they reduce these two waves together. Look at this picture. Pinholes are equidistant from S and are close to each other. Spherical waves spread out from S. Spherical waves also spread out from pinholes. Two waves received by such wave will be coherent and at superposition can interfere. In practice, the division of one light wave on two waves can be carried out by means of the opaque screen with the two small apertures. According to principle of Huygens-Fresnel, source S, look at the picture, creates in apertures of the screen sources of secondary waves S1 and S2, which will coherent. The first supervision of interference was carried out by Young, having passed a solar beam through very small aperture in the opaque screen. The second way of reception of coherent sources is based on reflection of light from two flat mirrors established under the angle alpha close to 180. This optical system is called mirrors of Fresnel. Imaginary images S1 and S2 serve as coherent sources of basic source S. Look at the picture, mirrors of Fresnel. The picture of interference arises in the point P. Next way consists in reception of imaginary image S stroke of the source S by the special single layer mirror, Lloyd's mirror. Sources S and S stroke can be considered as coherent. They create the interference picture in the point A of the screen A. For monochromatic light, the interference picture represents a number of alternating dark and light strips, maxima and minima. In case of white, not monochromatic light, maxima for different wavelengths settle down in the different places because of what interference strips extend and get iridescent coloring. Formation of coherent waves and the interference occurs also a head of light or thin transparent plate of film. Due to reflection of light from both surfaces of the film, there is a splitting of falling light beam, and there are conditions for interference of light. It speaks occurrence of iridescent coloring of soap bubbles, coloring of film of oily substances on surface of water or of wings of butterfly and other insects, coloring of internal surface of balls, feathers of some birds. Let's execute calculation of interference picture when two coherent waves from sources S1 and S2 pass different way, R1 and R2, and interfere in the point M. Look at the picture. It is between them arises a path difference. It's a delta. R2 minus R1. Geometrical difference of waves. If waves propagate in the medium with a refractive index of n, we can speak about optical path difference, delta. It's a small delta. It's product refractive index and path difference, n and delta. Look at this expression. Oscillation of vectors of electric intensity in the point M removed from sources and distance R1 and R2 accordingly from each source occurs under the harmonious law. And we can write down expression for electric intensity. Look at the next expression, E1 and E2. Addition of harmonious oscillation of one direction of identical frequency with a phases difference, delta phi. This delta phi, it's phi1 minus phi2. as it has been shown earlier, gives resulting oscillation of the same frequency. The amplitude of resulting oscillation of light vector is expressed this expression E in square. Look at this. And for the case considered by us, expression of E from the formula, look at this formula, follows this very useful expression. And let's determine delta phi, the last expression. Delta phi is equal to pi divided by wavelength and product delta. But delta is a path difference. And if light is propagated in the medium with a refractive index n, we can write down delta phi. Delta phi is 2 pi divided by wavelength and product delta. But, delta is the optical path of difference. We shall receive expression for electric intensity. This one, look at this expression, and two conditions for interference minima and for interference maximum. Delta is a path difference using k. It's a 0, 1, 2, 3, etc. and wavelength. And for maximum, delta is k and wavelength. The delta is a point where delta is equal to odd number of length of half waves. It is this expression value is a cos delta phi divided by 2 is equal 0, and the amplitude of resulting oscillation is equal to 0. In these points are formed interference minimum. If the difference of paths is equal to even number length of half wave, or to the integer of length of waves, we get interference maximum. Then talk about diffraction of light and diffraction of light on a solid or in parallel beams. At propagation of waves in the medium containing heterogeneity, the phenomenon of diffraction is observed. Diffraction is bending by waves of the obstacles meeting on their path, or in more comprehensive sense, diffraction is any deviation of advance of wave near to hindrances from law of geometrical optics. The opportunity of supervision of diffraction depend on a parity of wavelength of light and the size of obstacle. The phenomena of diffraction is shown more strongly if the size of an obstacle slit are comparable to length of a wave. Look at the picture. The passage of light through an aperture of small size. The phenomena of diffraction of light naturally is not observed almost because the size of the most part of bodies environmental as are incomprehensible to the wavelength of light. Owing to diffraction, the shadow image of object cases to be similar to the subject. In experience, diffraction can be observed at the formation of shadow from an obstacle is thin wire or hair, and also at passage of light through an aperture of small size. If between the screen and a source of monochromatic light S, to place other opaque screen A with a small aperture D, the border of the geometrical shadow will not be sharp. It is especially appreciable when the size D of aperture is very small in comparison with the distance L from the screen up to the aperture, and D more less than L. Then the stain on the screen will be submitted as a system of the alternating light and the dark rings gradually passing each other, grasping the area of geometrical shadow and also living for its limits. It speaks about not rectilinear propagation of light from the source S, about bending of light waves at edge of aperture in the screen A. At use of white light diffraction picture gets iridescent coloring. Diffraction of light speaks occurrence of iridescent rings around of light source when air is setted with fog or dust, coloring of pears. Diffraction is defined by wave properties of light, and to explain this phenomena is possible by principle of Huygens-Fresnel, according to which points of medium of which were reached with the front of wave are source of elementary secondary waves which are coherent. Let light from the source S falls on the screen through the round aperture AB. This second picture in the screen. Each point of side AB of front of light wave S1 is a secondary light source. Secondary sources are coherent, therefore beam proceeding from them 1, 2, 3, 4, etc. will be interfere among themselves, depending on path difference of beams on the screen. A in the point C, D, etc. Will arise interference maxima and minima. It has ring shapes diffraction picture. To define result of a diffraction in some point of space, it's necessary to calculate according to principle of Huygens-Fresnel the interference of the secondary waves which have got in this point from a wave surface. For a wave surface of the any form, such calculation of difficult. But on occasion, the spherical or flat wave surface or symmetric arrangement of a point concerning wave surface S1 and opaque barrier A, calculation are simple. The wave surface thus is breaking on separate sides zones of Fresnel that simplifies mathematical calculation. Let's consider result of diffraction of flat monochromatic waves on the slit which have been cut out in the opaque barrier. Look at the next picture, and having constant width BC is equal A. Wave falls normally to slit as a plane parallel bunch of light. All points of the wave surface opened by the slit are the centers of the secondary waves extending behind the slit in all directions. To represent all these secondary waves is impossible, therefore, on a picture are shown only secondary waves extending under the angle phi. Beams diffract under the angle phi will be collected in the point M of the screen and interfere. At phi is equal 0, all waves will come in the point M0 in the identical phase and will strengthen each other. On the screen will appear the most light strip, the center maximum. To define result of interference at phi not equal 0, from the point we shall lead perpendicular B D to the direction of branch of secondary waves. Optical waves of beam from B D up to point M. All the screen are identical. Length L of additional path difference does not bring. Therefore, the path difference DC of extreme beams is equal. Delta is equal A sin phi. We break DC into the pieces equal to wavelengths divided by 2. Generally, this path difference contain M half waves. And A sin phi is equal integer waves of wavelength divided by 2. Let's lead from the point D stroke a straight line D stroke A parallel of BD, and we shall divide BC into 2 equal zones of Fresnel. To any secondary waves going from any point of one zone of Fresnel, it's possible to find in the next zone such secondary waves. That the path difference between them will be wavelength divided by 2. For example, the secondary wave going from the point C in the chosen direction passes up to the point M distance on wavelength divided by 2 more than the wave going from the point A, etc. Hence, the secondary waves going from to next zone will extinguish each other since differ on the path on pi. The number of zones staked in a slit depends on length of wave, lambda, and angle phi. If slit BC is broken at construction on odd number of Fresnel zone, and M is equal to K plus 1, and DC on odd number of the pieces equal to wavelengths divided by 2 in the point M is observed diffraction maximum. It is A sinus phi is equal to K plus 1, and product lambda divided by 2 is the order of the maximum. Condition of diffraction minima is this expression. A sin phi is equal to K lambda. On the figure is we can see the case when M is equal to that corresponds in the point M to the diffraction minimum. This on the screen, the system of light maxima and dark minima strips symmetrically located to the left and the right from central. Phi is equal 0. The brightest strip will turn out. Intensity I of other maxima decreases on a measure of removal from the central maximum. If the slit is shined with white light on the screen, is formed the system of color strips. While only central maximum will keep color of Fresnel light is as at phi is equal 0, amplify all length of wave of light. And diffraction grating. Diffraction spectrum. Diffraction grating is an optical device representing a glass plate on which by the diamond edge renders plenty of parallel lines with an interval between them. The intact glass between lines serves as slits of the grating. Total width of the slit A, look at the picture, and interval B between slits is named the constant or the period of diffraction grating. D is equal A plus B. The best diffraction grating have up to 1,200 and 1,500 slits per millimeter. N is a general number of lines of diffraction grating. Let's consider diffraction of flat monochromatic wave falling normally on the diffraction grating. If on the grating falls the beam of monochromatic beams, the secondary waves going from slits on all direction are coherent and will interfere, forming a diffraction picture. If between the screen and the diffraction grating to place a collecting lens L, The screen is located in the focal plane of the lens. There is a diffraction picture with is growing out of two processes. Diffraction of light from each separate slit and interference of light from slits. The basic features of this process are defined by the second phenomenon. Let's consider the beams falling on the left edges of slits. N is equal 3. Okay. Calculate. 1, 2, 3. Due to diffraction, light from slits will propagate it in every possible direction. The path difference of beams from extreme points of two next slits and diffracting on the angle phi is defined. Delta is equal d multiply sin phi. If this path difference will be equal to 0 or an integer number of a wavelength. At interference, there are main maxima for which the condition satisfies. D sinus phi is equal k lambda, where k is the order of the main maxima. K is equal 0, 1, 2, 3, etc. At performance of the condition, d sin phi is equal 2k plus 1 and multiply wavelength divided by 2 will arise interference minima. Maxima will symmetrize concerning central. K is equal 0. Look at the picture. And phi is equal 0. Expression d sin phi is equal k lambda, named the basic formula of diffraction grating. Possible number A maximum is limited. It cannot be more than d divided by lambda. Between the main maxima are formed minima additional, which number depend on a number of slits of a grating. Between the main next maxima is settled down n minus 1 additional minima. On the picture, distribution of the density of maxima on the screen for the grating with n is equal 3 is shown. At plenty of slits, separate additional minima practically do not differ, and all space between the main maxima looks dark. As the amplitude of light oscillation in maxima is proportional to number of slits, intensity of maxima is proportional to the square of number of slits, n in square. Then is more number of slits of a diffraction grating, then the main maxima are especially sharp. Its amplitude of electric intensity proportional to n, intensity I proportional to amplitude in square, and I proportional n in square, number of slits. If on a grating falls white light for all values of wavelength, position of maxima of 0 order coincide. Its k is equal 0 false and phi is equal 0. Position of maxima of higher order will be various. More lambda than is more phi for the given value k. Therefore, the center maxima will look like a narrow white strip, and each of lateral maxima represent multicolored strip of a certain width. All spectra are symmetric concerning 0 maxima and are inverted to it by short wave violet age. The most intensity is a spectrum of first order. K is equal 1. This diffraction grating decomposes complex light into a spectrum, and consequently, with the success is applied in a spectral devices. For example, in a diffraction spectroscope, it's the device employed to measurement of length of light waves. It is for carrying out of the spectral analysis. And now we talk about polarization and dispersion of light. Polarization of light, natural and polarized. Malus law. The electromagnetic wave emitted by separate atom can be represented as the oscillation of two mutual perpendicular vectors of intensities of electric E and magnetic H fields. Both vectors change in the plane perpendicular to velocity vector. Such electromagnetic waves is called plane polarized. By reviewing a phenomenon of polarization, we further shall conduct all reasonings concerning of vector E, as experience and the theory shows that chemical, physiological, etc. action of light on material are stimulated mainly by vector E. Light from the sun, from filament of bulb, etc. is unpolarized, natural. In such light, vectors of E from the different elementary radiators have various orientation of oscillation. Projections of vectors E of natural light in the plane perpendicular to velocity will look like in the picture or A. All orientation are equiprobable and the amplitude of waves are equal in all directions. If there is a preferable direction of oscillation, such light is called partially polarized. It's picture B. Natural light is possible to turn into polarized. It is to polarize with the help of devices called as polarizers. The diagram of linearly polarized light is presented on picture C. Polarizers are capable to pass only component of vector E lying in the certain plane P stroke, called as a principal plane of polarizer. Look at the picture 2 and P, this direction P and the P stroke. Thus, through the polarizer pass polarized light, which intensity is equal to half of intensity of incident light. Its I intensity is equal. It's a natural I divided by 2. At rotation of polarizer concerning of the ray of natural light, the vibration plane of plane polarized light rotates also, but intensity of it does not change. The polarizer can be used for analysis of polarized light. Then it's called as the analyzer. of the plane polarized light fall on the analyzer of intensity E0. It passes only component E is equal E0 cos phi, where phi is the angle between the principal plane of the analyzer and the polarizer. As the light intensity is proportional to square of amplitude of oscillation, then I is equal I0 cos phi in square. This equation is Main's law, where I 0 is intensity of the plane polarized light, which has left polarizer. I is the light intensity which has left the analyzer. It's a malus. Malus law. Property from this equation that at rotation of the analyzer concerning the beam, intensity of light which has left the analyzer is the change from 0 up to I0. If at rotation of analyzer concerning the ray intensity of light which has left it does not change, the incident light is natural. If light change under the law of malus, then light is plane polarized. Eye of person is not capable to distinguish polarized light from natural, but approximately 25 or 30% of people have this ability, so almost never suspect about it. And talk about polarization of light at reflection and refraction on a border of two dielectrics. If the angle of incident of light on the border of two dielectrics is not equal to 0, the reflected and refracted rays appear in the part polarized. In the reflected ray oscillation perpendicular to the plane of incident prevail. Look at the picture A. The natural ray is conditionally designed by alternating arrows and points. Unpolarized light, look at this. This 1 median and first median and second, and this unpolarized, and these arrows show you it, and partially polarized light. This perpendicular to plane of paper, this point, and degree of polarization depend on the angle of incident of ray and on the refractive index of reflecting medium. At angle of incident satisfying to the requirement, it's a tangents theta b is equal n, where n is a refractive index of the second medium. Concerning the first, the reflected ray is completely polarized. Refracted is in part polarized, but degree of its polarization the greatest. This equation is a Brewster's law. Angle theta b is called Brewster's angle. It's easy to test that is falling of light under the Brewster's angle. The reflected and refracted rays are mutually perpendicular. This the border of two dielectrics, or a dielectric and a vacuum, is a polarizer. The polarity effect of reflected light is used, for example, at detection from air of a film of petroleum on water plane. The Brewster's law is unapplicable in the case of reflectance of light from a surface of conductors or metals. It's possible to achieve that the refracted ray will be completely polarized. For this purpose, polarizer is used. The pile of the glass plates located one after another. At realization of the Brewster's law, the degree of polarization of refracted ray will increase in accordance with the transit of plates. And talk about polarization at birefringence, double refraction. At transit of light through some crystal, the light ray is parted on two rays. This appearance has received the name of birefringence. Look at the picture. One of ray fulfills to the Snell refraction law is called ordinary. For the second ray, which has been marked out B, E, which is known as extraordinary, the ratio sin theta incidence divided by sin theta refraction remains a constant and depend on the direction of ray incidence. The ordinary ray at normal falling of light on a surface of crystal pass not reflecting as it follows from the Snell refraction law. Extraordinary ray refracts. Crystals have direction for which ordinary and extraordinary rays propagate, not being parted and with equal velocity. This direction are termed as optic axis of a crystal. If such direction is one, crystals are termed anaxial, of two are termed diaxonic. Two anaxial crystals concern the Iceland sphere type of calcium carbonate, quartz, tourmaline. On the picture, this direction is shown by the shaped line. Plane which is taking place through optic axis and light rays is called the main plane. Both rays which have left a crystal are completely polarized in the mutual perpendicular planes. Oscillation of an ordinary ray are perpendicular to the main plane, and oscillation of extraordinary are in the main plane. Birefringent crystals immediately are not used as polarizer. However, from them produce special polarization prism. It's the nickel prism. In some crystals, one of ray is absorbed more strongly than another. This appearance is known as diffracement. The strong difference has crystal of the tourmaline. In it, the ordinary ray is practically completely absorbed on length of 1 millimeter, and light which has left is plain polarized. The same properties has the Polaroid. Its celluloid film in whom is lined the quantity of equal rendered crystal of herapetite. The layer of Polaroid depth of 0.1 millimeter completely absorbed the O-ray. Hence, the Polaroid can be used as a polarizer. High-quality polarizer is the polarization prism of nickel. Action of the nickel sets up on a biofreezing of the Iceland sphere. The nickel is the prism integrated by a special mode from Iceland crystal, cut almost on diagonal and pasted together by Canadian balsam, which refractive index is 1.550, lays between the value of refractive indexes of Iceland crystal for ordinary ray, and 0 is equal 1.658, and the extraordinary ray, and E is equal 1.486. It allows having pick up in appropriate wave angle of the prism to provide total reflection of O-ray on the border with Canadian balsam. This ray is absorbed by a black low plane of prism. The extraordinary ray goes out from prism parallel to low plane. And look at the picture, and we can see this E ray and this plane polarized light, and in this O ray, and this we lay absorber, like dark. Defect of the tourmaline and the Polaroid in comparison with the nickel is the bad wavelength characteristic. The white light after the transit becomes painted, while the nickel is transparent in the visual part of spectrum. Double refraction is explained by anisotropy of crystal. It is dependent of optical properties from direction. The majority of phenous crystal are optically anisotropic. In them, speed of light and hence refractive index varies on different directions. And now we talk about optical rotation polarimetry. At transit of the plane, polarized light through some material is observed rotation of the plane of oscillation of E. E is electric intensity. Such materials are termed optically active. To them belong crystal, quartz, film pitch, pure liquids, and solution. Light after escaping of material is a plane polarized, but the vibration plane of its vector E appears rotated on the angle phi. Optical rotation of the first time was revealed on crystal of quartz. For crystals, the rotation angle of polarization plane is proportional to the path L traversed by the ray in the crystal. And look at this expression. It's phi is equal alpha L. Alpha is a specific rotation. It is equal to rotation angle of polarization plane of material by the layer of unit length. It's accepted to express it in degree in millimeter per millimeter, degree per millimeter. Specific rotation depends on wavelength lambda of light in which observation is conducted. This dependence is called the dispersion of rotatory power. It's individual for each material. In solution, the rotation angle of polarization plane is proportional to the path of ray in solution, L, and concentration of active material, C. And look at this expression. Phi is equal alpha, C, and L. Alpha is a specific rotation, L is accepted the express in decimeter, C in a gram, in a centimeter, in 3, phi in degree. If concentration presented in grams in 100 centimeter in power 3 of solution, then we get phi, look at last expression, is equal alpha in the concentration and L divided by 100. Independence of direction of rotation of polarization plane, optically active material are sectioned into the right and levatary. There is a left and dextrorotary quartz, Saharum, etc. materials. Numerical values of rotation constant for both types are equal. Optical activity of materials is stimulated by asymmetry of their molecules, which are not having neither planes nor the center of symmetry. Optical activity of many biopolymer is stipulated in particular by causal frame of their molecules. All proteins built only from levatary amino acidic oddments. Apparently, because of its organic isomers, can strongly discriminate on physiological action. For example, the dextrorotatory nicotine is more toxic than the levatatory nicotine. Levatatory epinephrine rents more than strong hormonal action than dextrorotatory epinephrine. Except of natural optical activity, the material can have synthetic optical activity, which originates in its under effects of external action. For example, at additional of materials into a magnetic field, phenomena of Faraday. If between the crossed polarizers to locate optically active material, the visual field will brighten up. Again, to receive the dark field is necessary to rotate the second polarizer on the angle phi. Knowing specific rotation alpha of the given material length L, having measurement phi, it's possible to find C. Such method of determination of concentration of material is known as polarimetry or saharimetry. The devices used for this purpose are known as polarimeters. We have a laboratory work number 12. In this work, we use a saharimeter to determine concentration of unknown solution. And we use a solution of sugar, different solution of sugar. In the physics lab, half-shadow polarimeter are used. The optical scheme is represented in figures. Light from the light source S, looked from this, first passes the filter F, which separated the sodium D line from the spectrum. Next, before reaching the eye, the light passes the condenser K, polarizer Polaroid P, the faceplate FP, which divides the field of view into two parts. The test cell KL filled the liquid analyzer Polaroid A and a spyglass PS. The faceplate is an optical device which separates the light into two partial waves with different speeds, causes the phase difference, and then interferes them. In polarimeters, the half-wave plate, which is oriented so that the polarization plane of the polarized light is rotated by a relatively small angle. Look at the picture. In the picture, we can see the oscillation plane of E vector in the left and right half of the field of view of polarimeter. The telescope's field of view of the polarimeter, which is divided into two halves by a faceplate, at a different position of the main plane of the analyzer AA, is shown in a figure. Since the phase plate FP covers the left side of linearly polarized light coming out from the polarizer, only right half of the light falls directly on the analyzer. The left side of the beam passes the half-wave plate before reaching the analyzer. The half-wave plate rotates the oscillation plane of the E vector anticlockwise by the angle 2 delta is equal 7 degrees. In the uncovered half of the field of view, the oscillation plane of the E vector remains unaffected. The oscillation plane of the E vector is different in the left of right half of the field of view. According to the Malus law, the light intensity of the left side of field of view and the right side manifest as follows. Look at this expression. IT is equal I0 cos gamma in square. And the next expression for I2 with index 2 intensity. Here I0 is light intensity falling on the analyzer in each half of the field of view. On the left diagram, gamma is equal 90 degree. Gamma is equal 90 degree minus delta on the center of and gamma is equal 90 minus 2 delta on the right diagram. According two formulas. The condition of I1 is equal I2 is found only in two cases. First, when gamma is equal minus delta, and the second, when gamma is equal 90 minus delta. In the first case, both sides of the field of vision are of maximum brightness. In the second case, the minimum. Both states can be considered as zero position of the polarimeter. However, considering characters of the eye together with the changing light intensity, the measurement are made nearby. Gamma is equal 90 degree. Pi divided by 2. Rotating the analyzer by a small angle near pi divided by 2, there will be a considerable change of intensity in the health of a field of vision. Based on the foregoing, rotation angle of the analyzer is always measured in the polarimeter zero position, where both sides of the field of view are equally weakly light. I first is equal I second. Then the analyzer main plane AA is perpendicular to the bisection O of the angle to delta. In the further, we will name this position the zero position. Angle readings are taken from two symmetrically placed circular verniers of the polarimeter. One of them is shown with the main scale on the figure, this one. From the main scale, grades on half graded are taken, smaller parts from the vernier. It's important that readings must be taken with accuracy of the vernier. We can see the reading in this picture. We can see the reading 2.24 degree. In medicine, the polarimeter is used for determination of saccharum in urine for biophysics researchers. By this method, it is possible to distinguish dextrorotary variations of materials from levorotary. For example, levorotary chloromethylene is the fissile antibiotic, while extra-rotary chloromethine has no medical properties. Use of dispersion of rotation gives good outcomes at research of biopolymer. It's very sensitive to any change in molecular composition. And to talk about dispersion of light. Dispersion of light is called the phenomenon caused by dependence of refractive index of material from frequency of light wave. In most cases, on the border of two different transparent medium, the short wave radiation reflects more strongly than the long wave radiation. Distribution of any radiation on lights of wave is known as spectrum of this radiation. By corollary of light dispersion is decomposition of white light to spectrum at passage through a prism for the first time explored by Newton. To explain dispersion is possible as follows. Under action of transiting electromagnetic wave, electrons of medium start to make the harmonic forces oscillation with frequency equal to frequency of the transmitted wave. Oscillating electrons radiate secondary waves of the same frequency. Between the primary wave and the secondary waves, the phase shift is formed, caused by retardation of oscillation of electrons. The resultant wave is dephased also in comparison with the initial and consequently has other speed of propagation. This phase shift depends on the oscillation frequency of electromagnetic field. It is light of various length of waves will have different speed of propagation v and so different refractive index n, as n is equal c divided by v, where c is the speed of light in vacuum. The least refractive index will have a red color and greatest is violet. For all transparent colorless material, function n as a function of wavelength is shown on next picture. With decrease of wavelength, the refractive index in the beginning is incremented. The quantity dn divided by d lambda is known as dispersion of material. If its ratio more than 0 on part AB, such dispersion is called the normal. At very small length of waves apart, where this ratio more than 0 can appear. Such dependence n from lambda is termed as abnormal dispersion. The abnormal dispersion is observed on the part of length of waves where there is light absorption that corresponds to a resonant requirement omega is equal omega 0, where omega is a frequency of a transmitted wave. Omega 0 is a natural frequency of oscillation of electron of medium. The abnormal dispersion enable to find frequencies of aging tones of electrons in atom and molecules, and on this basis to judge their structure. The phenomena of dispersion in various optical systems plays positive and negative role. In lenses of cameras, microscopes, dispersion of light produced chromatic aberrations that worsens the image. As at chromatic aberration, the luminous point emitting the white light look like the iridescent stain. And they talk about spectrum analysis. On a line spectrum of streams of any materials, it's possible to establish what chemical elements enter its composition. Such method of definition of chemical composition of material is termed as qualitative spectrum analysis. Precise location of lines in the radiation spectrum of each element is given in express tables of spectral lines. The spectrum analysis of gases can be carried out and on absorption spectrums. The method of the quantitative spectrum analysis permitting on intensity of light emission of length of chemical element to determine its percentage in AC designed. It allowed to find the presence of very much mass of element up to 10 in power minus 6 and 10 in power minus 9 gram. For definition of element with lower excitation energy, 2 or 4 electron volts is used the photometry of flame. The abbreviated plane is on a picture. For the light guide on a photoelectric cell connected with a sensing galvanometer. Having a gang of replaceable light filter, it's possible to study various fields of spectrum and to establish whether there is any elements. In a flame with major precision, defined all alkaline and alka earth elements, manganese, chromium, etc. Photometry of flame is applied to the analysis of connatural water, biological fluids, chemical fertilizing, and medical specimens. And now that's all. And your homework. Read a lecture and take the test after lecture in 2 weeks. I will open the test for you tomorrow, and I will open a lecture at PDF format today. Thank you for your attention. See you next lecture. Goodbye.